Okay, so in the past, like maybe 10 videos I've made, I have explored the gamma function a lot. I've connected it to other functions, such as the beta function, which is its older cousin, I would say. What else? There was the polygamma functions, including the digamma function and the trigamma function, which are just nth order logarithmic derivatives of the gamma function. Well, now I want to connect it to something very important and fundamental in analytic number theory, which is the Riemann zeta function. So there's this alternate definition for the Riemann zeta function that is in terms of the gamma function, so it's 1 over the gamma of s, and an integral. So this integral is the integral from 0 to infinity, x to the s minus 1 over e to the x minus 1 dx. This looks kind of hellish. First, because it doesn't have an elementary antiderivative because of this s in the top, and I'm not sure if it would, even if the power were a constant. Okay, so this is pretty important. So we're going to go ahead and derive this. Let's start by trying to multiply the zeta function and the gamma function together, if that was the way I did it. Yes. So when we multiply them together, what do we get? We get zeta of s times gamma of s. Zeta of s is just this sum right here. So n is greater or equal to, sorry, not 0. It is defined as being 1, starting at 1. And then 1 over n to the s power, so that's the argument. Okay, and then we have the gamma function, which is the integral from 0 to infinity, t to the s minus 1, e to the negative t dt. Let's go ahead and interlace the two and see what happens. So, only way we can really do that is by bringing this power into the integral. So, and maybe interchanging the order of integration and summation. But for now, I'm going to leave it be. So the sum's going to stay on the outside. I'm going to have the integral sitting right next to it. And then t to the s minus 1 over n to the s. Okay, so importantly, here we have a t to the s. Here you have an n to the s. We can actually combine the two. So this t to the s and this n to the s, just combine the bases, we get t over n all to the s, e to the negative t dt. Except for one problem. Remember that the t has this negative 1 in the power, so let's just multiply that on the side. dt, and then over t, so that can just be t to the negative 1. Okay, so that's looking a little bit better. How do we make it look even nicer? Make a substitution. If we go ahead and let u equal to t over n, well, let's isolate t first, so we get nu is equal to t. And then now let's find the differential element. When you find the differential of either side, the n is going to stay on the left-hand side. The differential of u is du. The right-hand side is just dt. Okay, so that's basically it. Now let's take the sum once again. N is greater or equal to 0. All right, bounds for this integral. We'll see here that t is equal to 0. N is not 0, so this is always going to be defined as 0. So the lower bound is going to be equal to 0. And then upper bound, when t is infinity, as long as n is not negative, so it's not going to change the sign, then u will also be infinity. And obviously n isn't negative. It is, okay, this should not be 0, this should be 1. It is greater than or equal to 1. So that's nice, the bounds stay the same. T over n is just u, so we have u to the power of s, e to the negative t, which is nu. Dt is just n times du, so we have that. The denominator t is just nu. So these n's are going to cancel each other out. So that's still going to be the same. It's still going to be du over u. All right, and that looks so much cleaner now because you no longer have this divisive base. So now let's go ahead and interchange the order of the sum and the integral. Why? Because of this guy right here. Okay, so by dominated convergence, we get to interchange the two. So the integral is now on the outside. Now, this u to the s, we could keep it on the inside of the sum, but we don't need to because it doesn't have an n inside of it. It is independent of the index variable. So we could just take it to the outside. And same deal with this u right here. In fact, we don't even need to write it here anymore. We can just write it as u to the negative 1, which we can combine with this right here. So that could be u to the s minus 1. So that's gone. Only thing that contains an n in it that we need to worry about is this exponential right here. So the sum is going to come in, okay, and it's going to apply to just the exponential only. And then the du is going to close off our integral. Now, why is that something that we want to do? It's because of the geometric series, okay? Remember that if you take the sum as n is greater than or equal to 0 of x to the nth power, then you're going to get 1 over 1 minus x as long as x is inside of the range negative 1, 1, open, so it cannot equal to 1. Well, in here, n, we can rewrite this as e to the negative u raised to the nth power, right? So e to the negative u is analogous to our x. The only difference now is that this starts at 1, this starts at 0. We'll take care of that in a second. First, we have to check if this really converges or not. Well, x has to be between negative 1 and 1. Is e to the negative u between negative 1 and 1? Well, when u is equal to 0, the inside approach is 1. But that's going to be a limiting case because obviously this is an integral. So yes, it does converge. But what about for the upper bound? If you plug in e to the negative infinity, it's going to go to 0. And that is obviously on this interval right here. So this does indeed converge. And this is decreasing the whole way. So it's going to stay on that interval. So now what? Convert that into something that looks more like this. And then you can see that this is very close to being done because it already kind of looks like the integral that I showed you guys earlier. Okay, now, let's just work on that by itself, actually. So n is greater or equal to 1, e to the negative u to the nth power. Well, this is greater than or equal to 1. Here, it's greater than or equal to 0. But notice that the only difference is the first term where n equals 0. So we can do this. We can just add that on. So that'll, in a way, make the index be starting at 0, right? So if there were an n equals 0 term, then if we plug in 0 there, then anything to the power of 0 is just 1. So yes, this right here is now what the sum would be if it started at 0. Okay, but we still want to keep it equal to this right here. So we added on 1 to make the inside look more like this. But we have to subtract it away now so that it stays equal to that. Okay, so this right here, this whole thing is just equal to this, and this inside part, well, we can apply this formula now because the indexing starts correctly. We made up for it. X to the nth power is just the sum over x to the nth power is just 1 over 1 minus x. So in our case, that's going to be e to the negative u. Great. So this right here is we're going to copy the integral down. We're going to have this u to the s minus 1. Okay. This whole thing is going to be that. So I'm going to, give me a second. U to the s minus 1, I'm going to copy down on the side. This right here is just this minus that. So 1 over 1 minus e to the negative u, okay, minus 1 du. All right. Okay. So now what we can do is combine the two. This negative 1, we can go ahead and just rewrite as, actually, I'm going to keep this here. Let's do this work below it. So 1 over 1 minus e to the negative u. This negative 1, I'm going to write as 1 minus e to the negative u over 1 minus e to the negative u. Okay, these two cancel to make 1. Now, when you combine the two fractions, 1 minus 1 is just 0, and the double negative e to the negative u is just e to the negative u, and the bottom, the denominator is going to stay the same. All right. And the final step is to expand by e to the positive u. When you do that, e to the negative u just goes to 1 because they're multiplicative inverses. And then over 1, this 1, when you multiply by e to the u, is just going to go to e to the u. And then once again, this right here is e to the u's multiplicative inverse. It's going to just return 1. So all in all, when you multiply the zeta and the gamma function, so I'm going to write that down here, zeta of s times gamma of s, this is going to result in this integral from 0 to infinity. On the top, I'm going to write this u to the s minus 1. On the bottom, I'm going to write e to the u minus 1 du. And there you go. So how do we get back to the form we had in the beginning? Divide by gamma on both sides. So zeta of s equals to 1 over gamma of s times integral from 0 to infinity u to the s minus 1 e to the u minus 1 du. And yeah, there we go. I'm going to get rid of this. And we can box the final answer. Yeah.